Think about it, and you need to look at one of the tables here. And you need to look at, no, not at this one, you don't need that one. First of all, you got to ask yourself, Cl minus, what happened here? Okay? And then you want to pull that electron off again. Want to pull it off. I'm enjoying myself tremendously when I teach you. You are my future. You're going to pay in for my retirement. You're going to be the best, highest earners. And you pay a lot of taxes. Okay. Ooh. Okay, let me try a different way. So in order to make it, you have a Cl atom, a chlorine atom, okay? And now, chlorine obviously has electron affinity. That's what I explained at the beginning. Chlorine has electron affinity. These guys have electron affinity. They like to be anions. They like to pull an electron off something else, like to take an electron on, and with this they are negatively charged. So what they do, they take that electron and go down in what? In energy. So what do? They release energy. Isn't that right? Okay. So electron affinity is right here. This is the electron affinity, EA. This is obviously the amount of energy that they release, okay, when they pull that electron off. So what kind of energy would they need when they add that electron to the system? What kind of energy would they need in order to pull it off again? Why don't we discuss this with each other? You are ionizing this, okay? You're ionizing it. And ionizing is always to take an electron away. What is it? No. What is it? No. Don't let me down, please. Okay, let's do that again. All right? Now, seriously now, okay? Electron affinity. Electron affinity is the energy that is released by an atom when it picks up an electron and becomes negatively charged. And this is a negative sign, is that right? And it's also a green number, all right, just for you. It's a green number. So that is, what is that, the number? Say it in chorus, please. Minus 349 kilojoules per mole. So now you have that electron on there. Now you want to pull it off again. What kind of energy do you need to pull it off again? Okay, why don't you discuss this for 1 minute with each other? It's Friday, yeah, hard week. Guys in the morning had this like this. They were fresh. About 4 before, 4 to... What is it? No! What is it? Yeah. When I give you the solution, you will bite yourself in somewhere. But you need to understand this. If you don't understand this, you're getting lost. Okay? Not really. This is Berkeley here. All bright people. The comment was it's a very tricky question. I don't think so. Yes. Yes. Oh, we succeeded. Okay, good. Now, so I told you, electron affinity, it releases 349 kilojoules per mole, minus 349. Now it has this electron stuck to its atom, okay? All right. Now you want to remove it. You need the same energy that it released. You need to take on and to pull it off again, okay? And this is ionization energy is plus, so it only can be plus 349. All right, good. Everybody nearly got this. Everybody nearly got it. Oh, there's even a solution. Okay. Ionization energy and electron affinity. There we have it. Electron affinity. What was that? What ion did we have? We had chlorine. Okay. We make Cl minus. The chloride ion was 349. It was this one. So we have this one now. And now to pull it off again, we need the same amount. Nothing up here. Okay. We need the same amount to pull it off. But this would be if I have an X without an extra electron to pull that electron off that atom. But here I have an ion to pull that electron off. I need only 349, the opposite of this here. Okay. You got it? Good. Excellent. And actually the answer is even right here. Okay. So that's we skip this here. This is usually, you see the ionization energies here, but the electron affinities are here not very, at the beginning of the periodic table, not very large. They become larger here in oxygen, fluorine, and then what's this down there? Okay, never mind, somebody said minus 53. So let's say, what, is there a question missing? No. We are going to talk about the atomic radius. The atomic radius. The radius is just like you can't really determine the size of an orbital where the electron is. It's also, except if you have a solid compound, then you can measure the radius between the radii between two atoms. But this is sort of an approximation. It cannot be exactly measured, but you can measure it to 90% in gases, for example, or liquids. You can estimate it, you can measure it. So you measure the distance between atoms and compounds, okay? If you have crystalline compounds, of course, that's the exact radii then. But if you have gaseous compounds, you can't measure this very well, or liquid compounds. And so the idea, this is the distance, is twice the radius, and this would be the radius, okay? Now let's talk about how the radius behaves let's see, we go to the second period, and we go from left to right, from lithium to neon. So we're adding nuclear charge, and we also add electrons. So what do you think would happen to the radius? Does the radius become bigger as you go from left to right, or smaller? Smaller. The point is, the nuclear charge wins, okay? The nuclear charge wins, it pulls the electrons tighter a little bit, okay? And it pulls it quite a bit tighter. So this is in picometers, the atomic radii. Picometers is what? 10 to minus 12 meters, okay? Now, if I have 152 picometers, this is 0.152, what meters? Nanometers. And I always said an atom is about a tenth of a nanometer, something like this. That's closer to 2/10 of a nanometer, or 15.2 angstroms, but this is something you don't need to know. Okay, so you see, rightfully you see, as you're within the period, it pulls it closer. It pulls the electrons closer. With this, the radius shrinks, okay? But, of course, in the second period, it doesn't shrink that much anymore because you have all this stuff in between, all these electrons in between, all right? Same thing, just like with ionization energy. No. And so, but it goes up here within the, what do you call this here? The group, within the group, it increases, of course, because that's one period higher, then this is higher, this is higher, this is higher. Of course, you have all these electrons from these periods in here, so this got to be bigger, and that effect is not quite as pronounced anymore. All right, so you go from left to right, the atomic radius decreases, and from top to bottom, so within the period, the radius decreases, and from top to bottom, of course, it has to increase. So let's do something retroactive for you, okay, what we had talked about. Just to clear your mind from energies now, and let's do a little bit more energies. Which of the following has the smallest ionization energy? The chloride anion, the argon atom, or the potassium cation? So what I would recommend to you, that you write yourself down the valence electron configuration, the outermost orbitals. Write those down, and then think about it. So this has an extra electron here, there's one missing, and this is just an atom. So why don't you think about this and give me your answer? And then you say which one has the smallest ionization energy. Chloride, what is that? That's here. That would be a 3s2, 3p1, 2, 3, 4, 5, but you have an extra one, 3p6, isn't that right? Okay, now we remove one from here. What configuration would that be? Or what configuration would that be? Okay, and then you tell me which one hangs on the least to that outermost electron. How many are with me? Good? 2. You gotta be with me the second time around. Excuse me. Did I ever start this? Yeah. Oh, okay, good. Okay, there's some people say it's chloride, and some people say it's potassium. Okay, there's hardly anybody says argon. That's not a bad idea, actually, okay? So look at, obviously, can anybody tell me about their electronic configuration? Are they different or are they all the same? Yeah, isoelectronic, they have the same electronic configuration. Now, which one would hang on the least to one of its valence electron? The one with the least nuclear charge or the one with the highest nuclear charge? So why don't you answer this? And you give yourself a pat on the back if you discuss this right now. You can discuss it. Everybody in, or do you need the discussion still? I'm a little pressed for time. Everybody in, come on. I need to save some time here. I'm going to have a fun experiment. Everybody, click in, please. Can I close it? Everybody in? No, not everybody in. They say he closed it early. That's it? 419? Good. Yes. Where's the number here? Oh, they're still clicking. Oh, so, yeah. No, quick, make it all right. That's okay. Let's have some fun here. Yeah, okay, that was a phenomenal result, okay? So of course, let's be serious again, of course, these are all 3s2, 3p6, that's the valence electron configuration. Now the potassium is totally in a different period already, you can forget that, okay? But argon and chloride are in the same period, so which one has less nuclear charge? Of course, the one with the lower atomic number, this has 17 proton and this has 18, so this one doesn't hang on so that well to its negative ion there, and with this the answer was chloride. So I do this the next time. No, let's do this quickly. Which one, I give you 1.5 minutes and we answer it correctly if you're not right, which we do it. Which one has the smallest radius? Now we don't have any ions. Chlorine, argon, or potassium? Which has the smallest radius? Radius decreases and increases. Huh? He told you? Good. He's proud that he knows it. He wants to let you know. The question was, why are you telling me? Okay, now we have 40 seconds and then we do a nice experiment. I can't make fun anymore of this guy because he died, you know. Okay, everybody in? Many of them have left the building already. They've been ionized. Actually, they've been vaporized. Okay, yes, it's argon, of course. Argon, of course. And so, why, of course? They are not isoelectronic. So if you go from left to right, so this one, argon, is the smallest, and potassium is, again, in a new period, it is argon, okay? Now let's do an experiment, and then I explain to you what the experiment did. So we have here, in this cylinder here, in this gizmo here, Karen mixed hydrogen gas and chlorine gas. This is H2 and Cl2. And she mixed it if it forms hydrochloric acid, or HCl in the gas form, and the chlorine, holds the electron of the hydrogen. The hydrogen wants to be positive, the chlorine negative, and so we're going to get this started with a laser, and I have a green laser here. You ready now? No? Don't go away, it will be fun. So I have a green laser here. Ready? We're filling the hydrogen and the chlorine gas in there. We only can do this in 2 minutes, no problem. You let me know when it's okay. Ready? No? We could have done another campus. Ready? Ready. Driving her crazy. So we ignite this with a laser. I have a green laser here. Exciting. We still make it. We still make it. Ready? One more. What happened? No. See, I shine this green laser in here. Nothing happens. So obviously I don't have enough energy. But fortunately I have a blue laser here. Okay? There's a blue laser. You see that? You see the blue laser here? Yeah? Can you have the whole picture up there? See the blue laser? So what I'm going to do is I'm going to block it with my hand here now. And what happens if I remove that hand? We made HCl, hydrogen chloride. Are you guys ready? It will be loud. Like magic. I see you on Monday.